In this video, we're going to go over kinematics, specifically kinematics in one dimension, and some of the main topics we're going to go over are velocity, acceleration, and kinematic equations. Let's first go over velocity. So, I want to make a clear distinction between velocity and speed. Velocity measures how fast something goes in terms of displacement, and speed measures how fast something goes in terms of distance. So velocity is judged off of its final and initial spot difference, while speed measures the entire process of the object traveling. So the equation would be the velocity is the final displacement or spot minus the initial spot over the time elapsed, which is the time it took to travel that length, while the speed is the final distance minus the initial distance over the time elapsed. Now, also one thing to point out is that speed doesn't have a direction, but velocity does. So let's take an example here. So you start off at, let's say that an object starts off at 0 meters, and it travels all the way to 70, and it comes back to 50. So in this case, when we're trying to find the velocity of the object traveling in this distance, going from 0, reaching 70, and returning back to 50, the final spot is 50. So to find velocity, it will be 50 minus the initial, which is 0, over the time elapsed, which is in 5.0 seconds. So the velocity is 10 meters per second. Meanwhile, if you calculate the speed, which is the total distance traveled, it's going to be 50 plus 20, which is from 50 to 70, plus the 20 again, which is on the way back, which is 90, which is the total distance traveled, minus 0, which is the initial distance, and all that's over 5, so the speed would be 18 meters per second. Now, velocity would be useful in finding the average velocity in between 2 points on a graph. So normally things won't travel at the same speed all the time. Like if you're driving a car, you're gonna speed up, slow down. So if you take a look at this graph over here, it's kind of not linear. To find the velocity of between these 2 points here, we're basically finding the slope between those two, and it'll be the average rate of change. It'll be the average speed increase from this point to that point if it was linear. This is basically found at like a slope where you take 2 points, you find the distance between them vertically and divide it by the distance horizontally. And that will give you how much meters it increased in this case because it's speeding up. It'll give you how much meters increased over the time it took this in terms of seconds to get that increase in meters. Now, another thing to take note of is instantaneous velocity. This is the velocity at a given point in time. So normally, in this example, it took 2 points to find the velocity, but when the velocity is given in a point in time, then it will require some. So let's do a graph over here. It will require like a tangent line to find that velocity at a point in time. So let's say this is the meters, the displacement, this is t in seconds. So let's say this is a car driving. The car goes forward for some distance and then makes a U-turn and come back to its original spot. So let's say we're trying to find the velocity at this point in time. Normally if you want to find velocity, you would have 2 different points. So let's say this one's over here. And when you get the velocity, which is going to give you the slope, this will be the average meters per second the car traveled. But if you want to get it closer, you graph it with this point over here, and that would give you a different slope. We keep on doing this until the 2 points are basically on top of one another. So let's say even if it starts off here, you can see how it's slowly turning positive, because at this point there's still some room for the car to move forward before turning back. So if we started off down here, we have a negative slope, a negative average velocity. That's not the case over here at that point in time, because that is when the car is still moving forward, so it's a positive velocity. So as you bring the second point closer and closer to the first point, you eventually get it on top of one another, and that is when you get a tangent line that's only touching the graph at one point, and that gives you the instantaneous velocity, which is basically the tangent line. So this is found with the velocity as well. It's just the velocity equation, but this is when the time approaches 0. So this is some calculus type stuff. So what you want is, as shown in this example, you want to get the distance between the time between these 2 points to be as close as possible. Because if you started off here, you're not going to get the velocity you wanted, because this one over here, the initial velocity is positive, while if you have the second point over here, or the velocity at that point in time is positive because it's still speeding up. But if you get this point here and you calculate the average rate, then it's going to be negative. But as you get closer and closer, the time it took between the 2 points is getting smaller and smaller. Eventually they're on top of one another, and that's where you get the instantaneous velocity. The second topic we're going to go over is acceleration. So acceleration calculates the change in velocity over time. So this means it calculates the extent of how objects speed up or slow down. So the formula is this definition in terms of formula, and that is the change in velocity over time. And the units might be a bit janky because it's like seconds squared, but if you calculate the units of this equation over here, it's going to be meters per second over second, and this second's actually second over 1. And when you math it out, and it's like when you divide, you multiply, it's the same thing as multiplying by its reciprocal, and when you simplify that, you get meters over second squared. So even though it's kind of hard to get that conceptually, it's more like, how do you calculate the change in speed or the change in velocity over time? So yeah. Also, because velocity is directional, acceleration is directional as well. So it depends on which side you set as positive or negative, and depending on acceleration's relation to velocity, it depends on whether the object is accelerating or decelerating. So if you set going right as positive and the acceleration is positive as well, then you're accelerating because they're both going in the same direction. But if you set the velocity as positive going to the right, but then the acceleration is going to the left, which is a negative velocity, then it's decelerating. That's like if a car is driving to the right, but then the change in speed is negative, so it's slowing down over time. That is when you have a negative acceleration, and that is deceleration. And in this case, if you still set going to the right as positive, but the velocity is going to the left, so it's a negative velocity, like if it's going in reverse, and it keeps on going faster and faster in reverse over time, and it has a negative acceleration, then it's still accelerating. So if it's going in reverse and it's slowing down the amount it's going in reverse, that's when the acceleration is going this way, so it's decelerating. So here's an example. Let's say a car accelerates in a straight line from rest to 35 kilometers per hour in 10 seconds. And we're trying to find the acceleration. So let's just draw a diagram. So let's say here's a little car, and it starts off resting. So the initial velocity, which we call v naught, it's going to be 0. And as it speeds up, it eventually reaches a speed of 35 kilometers per hour. So that's the final velocity. And this entire event takes place in 10 seconds, so that's the time. Now, we're trying to find technically it's implied that it's average. We're trying to find the average acceleration of the car. So we're trying to find the change in, technically, a car won't accelerate at the same speed over time. It might start off slow and then it goes faster at the end. So that's where we're finding the average. We're trying to find how much speed the car increases in 1 second. So what we do here is we put out the equation. So the change in v is the final minus the initial, or v2 minus v1, over the change in time. Usually you start off at time 0, so usually just t, because if it's the final time minus the initial time, which is 0, it'll just be the final time. So what we have here is we just plug in the values, 35 kilometers per hour, and over 10 seconds. Now you see how we have two different time units here, so we're gonna have to convert hours into seconds. Alright, so after we converted the hours into seconds, we plug it back into the equation, and we can simplify it. So this is what we get. It will be this value over kilometers per second squared. Now this looks like a really small number, but remember that the acceleration units are meters per second squared. So we could convert this into meters per second squared, and that'll give us 0.97 meters per second squared. So what this is saying is that the car increases by pretty much a meter per second in terms of speed, on average over these 10 seconds, to reach a speed of 35 kilometers per hour. Now this might seem little, but let's try converting 35 kilometers per hour in terms of meters per second. So I think what we could basically do is, because we have the velocity in kilometers per second, we could just convert this into meters, which would be 9.7 meters per second, and that's the total distance the car is traveling after these 10 seconds. So if we add 0.97 to the original speed 10 times, that's going to give us the final speed of 9.7 meters per second. Alright, now let's take a look at kinematic equations. So these equations just show the relationships between an object's displacement, velocity, acceleration, and time. And one thing to point out here is that acceleration is going to be constant. Now these equations are mostly used, at least in this chapter, where we're working with gravity as the acceleration constant. So that is when acceleration is constant, because it's like a gravitational constant. And yeah, so with all these equations, they use a lot of similar variables, but these all really depend on what you're given in the equation to solve for. So like you can't just plug you can't just randomly plug stuff in. So for example, this equation has time, but this one doesn't. So if you were given time and you're trying to find x, for example, these two are the only ones that have x in it. If you don't have time given to you, but you have the velocity and initial velocity and acceleration given to you, then, and also initial displacement, then you can use that to find. Also, just a quick note, there's also proofs to figure out how these equations come from, but I'm not going to go over that in this video. And it mostly just basically comes from the basic definitions of velocity and acceleration. One thing to point out is these two over here, number 1 and number 4, you don't really have to memorize those as much, as they are more of like easier concept to go over. This is just the average velocity. So normally we saw average velocity as like the change in x over the change in t over 2, or change in x over change in t. But in this case, if you're just given two velocities, you can just find the average between the two instead of calculating the change in distance between 2 points. But it basically gives you the same thing. And this one up here, this is the definition of acceleration, rewritten in a way that isolates v, so you don't really have to memorize that as well if you know the definition of acceleration. And it's mostly just these two that you have to focus on to get down over practice. So let's go over an example where we could use these kinematic equations. So let's say you drop a ball from 20 meters and it lands on the ground. How long does it fall for? How long does it take for the ball to reach the ground? Now, because this is a kinematic equation, or it's just like a physics equation in general, it's best to draw a diagram. So let's say you're on this cliff, and this is you with the ball. You drop the ball, and the ball travels a total distance of 20 meters. So its total displacement would be 20 meters, and that would equal to x, the total displacement. And we're trying to find the t. We don't know the t, but we do know some stuff that are implied. Because the ball is traveling 20 meters, we could just set the top before you drop it at 0. And since you're dropping it, you're not throwing it or anything, the initial velocity is 0 as well. There's also the implied acceleration in terms of dropping objects. In this case, it's basically gravity, and that is 9.8 meters per second squared. And this is positive or negative depending on which direction the object goes, and since the object's going down and gravity also goes down, they're both the same sign. And given all of this stuff, the only unknown in that equation is just t, and we can use this equation, x equals x naught v naught t plus 1/2 at squared, to solve for t. Now we could just plug these values in. Just have 20 meters, 0 for x naught, 0 for v naught, t, we don't know what t is. Since these two are 0, we could just cancel those two out. We could just simplify and to solve for what t is. Alright, so when we find the final answer, it takes the ball 4.1 seconds to fall down. Now, it's accounting for sig figs. It might look like there's 1 here because it's 20, but technically the 0 is significant as well. I probably should have labeled this as a significant value, because when we measure it, it's not going to vary between 10 or 30. It's going to vary between 19 to 21. So when we divide 2 sig figs by 2 sig figs, we're going to get a 2 sig fig answer. Now this is probably the most basic kinematics equation that could happen. Some other things can be more tricky. Like, let's say the dude throws the ball down initially at like 5 meters per second. So that means the initial velocity is 5 meters per second, and you substitute that into here for VO instead of 0, and that will lead you with a t squared value and a t value and a value with no t, or a term with no t, and you just have to quadratic formula that. There are other options where the guy throws the ball up, so I'm just going to draw a quick one down here, where he throws the ball up and it goes down. So in this case, if he throws it up at let's say 5 meters per second again, in this case the initial velocity is going up, and that goes against gravity. So in this case, you're gonna have set acceleration or velocity in opposite signs. Now normally, because he's throwing it, the majority of the process is going down, I would set acceleration as positive and the initial velocity is negative, and just solve it using this equation like that. And there's just another helpful tip, is when the ball goes up and it comes back down, the initial velocity is the same as the velocity, because it travels the same distance in the same amount of time. And up here, the velocity is 0. So the reason why the velocity is the same at the bottom and from the beginning to the end is because acceleration is constant. So it speeds up and slows down the same rate. The velocity increases and decreases at the same rate. So say like you start off, it's really quick, but then once you reach the peak, it kind of slows down and it speeds back up. And when you throw it up and back down, it's the same amount of distance traveled up as the same amount of distance traveled down, or displacement. The time it goes up is the same as the time going down. So the other kinematic equation used is v squared equals v naught squared plus 2a minus x naught. So x is total displacement. Now, if you go from the bottom to the top, that's when x is the distance traveled up. But if it goes down as well on the same spot, x equals 0, because that's the total displacement from beginning to end. And this kind of proves that the initial velocity is the same as the final one. So if x equals 0 as the total displacement, then we could just substitute this into here. And since the initial displacement is 0 as well, because that's what we're starting off with, we'll just get v squared equals to v naught. And this is 2a times 0, and this entire thing cancels out. And when you root v squared, what you're going to be left with is a plus or minus v equals v naught. And this is basically the same value. And like, for example, if in this part over here, if I put in 5 squared and negative 5 squared, they're going to be the same answer. 25 should have wrote meters per second. What this shows is that or in this case, the plus or minus, is that if the the velocity going up is the same as the velocity going down, but it's just in a negative direction. And that should be the basis for kinematics. And if there are any other problems that may be more challenging, it just requires drawing out the solution, drawing out the problem, and labeling what you're given, and trying to find the unknown by using the equations that fit all of the variables that you know or what you need to know.